All right, so we're going to look at Chapter 11 here. And Chapter 11 is looking at regression models. And regression models are our first step into really sophisticated tools of analysis because we're looking at the analysis of the variance between different properties. Now, simple linear regression, which is what we're doing in Chapter 11, is a precursor to doing an ANOVA because an ANOVA, or an analysis of the variance, is actually looking at the linear regression interactions of multiple variables simultaneously. So an ANOVA is simply a linear regression conducted simultaneously of multiple variables. So while I doubt we'll actually get to ANOVA in this semester, linear regression prepares you for the same ideas of the relationships of causation, correlation, and prediction using mathematical tools. And so the first thing we want to look at is simply going back to our earliest geometry that we did in grade school, where you memorize the formula y equals mx plus b, where m was equal to the slope of the line and b was the intercept between the x-axis and the y-axis and that line. And so you can see that this very simple formula draws a straight line between at least 2 points and then calculates the slope and the intercept as it crosses through the axis, and that gives us a formula then to calculate every position on that line. Well, when we're looking at linear regression, we're looking to see, can we draw a straight line between two factors? In other words, can I look at the way two factors interact with one another and draw a straight line into infinity where for any value of y, I could calculate a value of x, or any given variable of x, I could calculate the variable y. So there's a few things that we need to look here. Our basic equation for linear regression has this b naught, which is that y-intercept, and b1, which is our slope multiplied by x. And then we have to add in a factor of error because this error is taking a sample of data, not the population, a sample of data, and it's calculating a relationship between the two variables, which means that we may or may not be correct at all times. And so when we look at this model, we are looking at a response variable y as in something that is going to give us a result based on a predictor x. And so from this equation, if I know my interceptor and my slope, I can take any value of x and then find the corresponding value of y if they have a linear relationship. And that's the big if. That's what we want to test here. So when we look at linear regression, we can calculate these estimates using very complicated mathematical formulas that you thankfully will not have to do by hand. If you look in your textbook, you'll see the least squares estimate, and this shows the calculation of both the intercept and the slope based on all of your x sub i's, your y sub i's for all values of I equals 1 to n. But what we really care about here is understanding the relationship of the variance between each of those variables and how they relate to forming that individual equation. So while my top line equation here, y hat is equal to b naught hat plus b1 hat times x, that's my actual regression formula. And we'll show you what that looks like in Minitab in a second. But for every individual y sub I, there's an x sub I that goes along with that data point and a measure of error. And the measure of error is the difference between what the true values are and what the model would predict it to be. And when we have our time together this week on Thursday, we'll actually go through and calculate several of these y sub i's and calculate e sub I, because this is an important concept called the residual. And the residual is the difference between what our model would say happens and what actually happens. So it's the difference between our prediction and our reality. obviously we want that E to be as small as possible. We want reality to be as close to our prediction as possible because that means that our model is good, means our model works. If we have a large amount of error, then our model isn't very valuable, is it? Now, the sum of the squares of all of these residuals actually gives us the variance of the function. So if you remember from my hypothesis testing, that variance is really an important factor in looking at our hypothesis testing, and you actually can perform hypothesis tests in linear regression manually. It is a chore. Don't ever do it. You want to use Minitab. This is what Minitab was made to do, was to make it so you don't have to do this by hand. So you don't want to do it by hand, but you could if you had to. And so these are the formulas that Minitab will use to very quickly give us the data that we could calculate by hand, but we simply aren't going to take the time to do. So a hypothesis test for the slope is given a test statistic of b hat 1 minus this beta 1 comma 0, so our intercept there, divided by the square root of that calculated variance divided by the sum of the residuals for our x. We can also do a t-test by saying that if that test statistic is greater than t of alpha over 2 n minus 2, then we would reject that as being a relationship between the two variables based on the slope of the resulting formula. We can do the same thing for the y-intercept and again use the test statistic to reject the relationship if none exists. And then finally, you could do a special case where you're just looking to say, is there a significance of the regression? Does a linear relationship even exist? And in some cases, it doesn't. And so in those cases, you would have a t-test that shows that there is no regression at all. Now, looking at the residuals themselves, like I said, the residual is the difference between the prediction model from that equation we build and the actual reality. And so in this chapter, in your homework, in your case study 3, you're going to be using real data values to then verify your model against the given data to then calculate these residuals and see how robust your model actually is. A quick way to look at this is to create a normal probability plot of all the residuals. Again, this is what Minitab was made to do. It will do this for you very quickly. So the normal probability plot of the residuals, if it shows that the residuals fit a normal distribution approximately, and we'll talk about that again on Thursday, but if it fits a normal probability plot approximately, then we can assume that our regression is a good model and in fact robust. The determinant of our coefficient of determination, r squared, is the relationship between the residuals, the sum of the squares of the residuals, and the sum of the squares of the total equation, so both the slope and the intercept. This r squared value is another indicator, a quick indicator of a ratio between the residual error and the model overall. The higher the R2 value, the closer it is to 1 or 100%, which is what we get in Minitab. It gives it to you in the terms of a percentage. The closer we get to 1, the more robust your model. So, some important things to keep in mind. First, just because you have 2 columns of data that create a line doesn't mean you actually have a relationship. So for example, if I was comparing the number of potholes on the Lloyd between Newburgh and USI as a measure of every mile, and then I also looked at the time it took to bake pizzas and have the crust sufficiently done, I could collect 2 columns of data, run them against each other and show that there's a relationship that exists when logically you know that it has nothing to do with one another. So you want to be careful that you're using regression models on variables that you expect to have a relationship with. They already have some sort of interaction. In fact, that's one of the reasons we use the ANOVA, because ANOVA can actually show us interaction effects to validate that those two variables are in fact responding to one another. The other thing to remember is that just because you can create a model doesn't mean that it is predictive. We would like it to be predictive because once we have a predictive model, we can then anticipate how things are going to change over time. However, the smaller your sample size, the less powerful the predictive power of your model will become. The larger your sample size, the more robust your model will be. And so it's important to remember that you want to keep a large sample size, the largest that is feasibly possible, and that you're working with variables that you already expect to have a relationship. So when we use Minitab, the very most important thing to remember is that the null hypothesis is that there is no relationship. And so we want to reject the null hypothesis. We want the p-values for the equation to be less than 0.05 or whatever our alpha is. So if our alpha is 90, if our confidence level is 90, then we would want a p-value less than 0.1. If our confidence level is 95, we want a p-value less than 0.05. If our confidence level is 99%, we want a p-value of less than 0.01. We want to reject the null hypothesis because the null hypothesis is that no relationship exists. Now, when we look at the data, we're going to look at a few things. Minitab gives us more than we need, but we're going to look at p-values, the r squared, remember the coefficient of determination, and the actual equation that spits out. We're also going to graph the normal probability plot to look for normality and independence of the model. The analysis of variance table is not something that you need in this class because we're not actually doing full ANOVAs. However, that would be where you could find that sigma squared value because the sum of the squares of the error is listed in the analysis of variance section of your data output. The model summary is going to give you that r squared value, which again, we want it to be as close to 100% as we can get. The coefficients are actually going to give you your slope and your intercept for your actual equation, as well as your t-statistics and p-values. And that's where we're going to look to see that those p-values are less than the alpha given to ensure that there is a relationship here. And then the regression equation is the actual model that we would use to test other values and calculate residuals based on that. So what does it look like? Well, here you go, our regression equation. So we had data that was relating the sale price of houses to the amount of taxes that were being paid. And so we have sale, which would be our Y, is equal to M. So that's right there, that 13.2 plus, or I'm sorry, B plus mx. So if you remember our original formula, y equals mx plus b, that m that is talking about the slope is that coefficient before the taxes, and that intercept, the y-intercept, is the coefficient, and they call that the constant here. So what is our predictor? Our predictor is the taxes. Our predictor is the X variable. That's very important. If you're taking notes right now, you want to write that down. Your predictor is the X variable. What is your response variable? Sale. So when you go to put data in Minitab and it asks you for which column is the response data and which column is the predictor data, your predictor data is your X, your response is the Y, which means given a value for taxes, we could predict the sales price. Now, if you jump down to the next group, you see coefficients here. So again, these are the coefficients. So we have our y-intercept at 13.32, and we have our slope 3.324 in this case, so both of those pop up into the equation. We have the standard error of those coefficients, their t-value, and that would have been using the test statistic equations that were found earlier in the lecture and in your textbook, the ones that you do not want to be doing by hand, and then your p-value. And our p-value right here is what we're looking at to say, okay, is this less than alpha? In both cases, our p-value is 0, which is less than alpha, and so we reject the null hypothesis because the null hypothesis says there is no relationship. Based on these p-values, we say that there is a relationship, and the relationship can be modeled using the regression equation above. Finally, the model summary here gives us that r-squared value. Now that r-squared value, they actually give you 3 of them. The first one is the r-squared calculated using the formula you found in your textbook. The second one, r-squared adjusted, is Minitab going in and taking out data points that they think don't fit the model well. There's another grouping of data that I will show you on Thursday when we're doing Minitab together. That grouping of data, you'll see if we remove those data points, we'll look to see how the r-squared is adjusted based on removing those data points that don't seem to fit with the rest of the data. Finally, r-squared predicted is looking at what is its predictive value. So if I were going to use this to extrapolate new sales values based on tax information, how robust would that be? What we're looking here for an r-squared value, you definitely want it above 50%. I'd say really above 70% you're looking for. If you've got an r-squared in the 80 or 90%, you can feel really, really confident about that model. Because remember, this is a relationship of the sum of the squares of the residuals. So that difference between what the model thinks should happen and what the data says happened. And that relationship of those residuals tells us how good is this model at fitting all the data based on our sample. So 76.73, I'll take it. I'll take it. It's a fair model. P-values of zeros, there's definitely a relationship. Regression equation, that's what I needed so that I could make other predictive values. Last step, normal probability plot of the residuals. What I'd like you to do right now, nobody can see you, so don't feel silly. We call this the fat pencil test. And you just go ahead, pick up Sharpie, pen, pencil, hold it against that red line on your screen. If the pencil covers the majority of the dots, then you can go ahead and assume that that your residuals follow a normal distribution, which means, again, that your data has shown independence and is an effective tool at showing the relationship between these 2 variables. So that fat pencil test doesn't sound very scientific, but basically what it's doing is it's saying in all model building, we're going to have some outliers. So you see towards the top of the line and the bottom of the line, there's some outliers. That is to be expected. That's normal. But if the majority of the data points are close enough to the line that they could be covered by putting a pencil against that red line, then you know that you have a fairly normal distribution of your residuals and your model is fairly robust. If this didn't make a lot of sense to you, please read the chapter, go through the slides, watch the video again. We will take time on Thursday to go through this step by step, building the plots in Minitab, analyzing the data and putting it into the format that we're going to be using for case study 3 and also on the exam. And so understanding the data that is spit out of Minitab is really your job with this chapter. Not that you would be able to calculate it by hand, but that you would be able to interpret it based on the results that you're given in Minitab. And with that, I will see you all on Thursday.